Hey, what's up, guys? This is Cheng here. So, LeetCode number 2003. Smallest missing generic value in each subtree. Okay, so this is another tree problem, right? So we have a tree, right, and rooted from 0 to n minus 1, and then so the tree is given in the form of a parent array, where each value of the parent array is a parent of the current node, right? And so node 0 is a root, and the parent of 0 equals to -1. Okay, and then we have a 10 to the power of 5 possible generic values, right? Basically, that's each of the value. There's going to be possible values for each node, right? Okay, and then you're given this nums is a distinct generic value for node I, right? And then so our task this time is to find the smallest of generic missing value. So the smallest missing value for each subtree rooted as a node I. Okay, so the subtree contains a node X and all its descendant nodes. Right. So for example, we have this we have this tree, right? And then the nums for each tree is like 1, 2, 3, 4, 5, 1, 2, 3, 3, 4, right? Which means the value of node 0 is 1. So the value of node 2 is the value of node 1 is 2, right? So the value of node 2 is 3. For node 3 is 4. So that's why we have 5, 1, 1, 1. And why is that? Because for node 0, for node zeros, it includes both 1, 2, 3, 4, right? And so the smallest missing number for node 0 will be 5 in this case, right? Will be this one, okay? And then in terms of 1, 2, and 3, for node 1, node 2, and node 3. So for node 1, right? See, for node 1, the value is 2, right? So that's why the smallest missing value is 1, right? So for 2, 3, they are the same because obviously 3 and 4, then they don't include 1. That's why 1 will be their answer, right? And that's that. So here's another example here, right? And then for the last one, right? So this one is a special case because so for this one, so why we have all 1? Because 1 does not exist in any of the nodes, right? So if that's the case, apparently, right, if there's no 1 there, no, it means that every node will have 1 as the smallest missing number. That's pretty obvious, right? And then the constraints are like this, right? Each number is distinct. So for this one, so the brute force is what? So brute force will be for each of a node, right? We'll do a DFS for each of the node, right? And then for each of the DFS, we can get all the possible numbers for the subtree, right? And then we just scan from the smallest to the biggest, and then we find the first missing number for each subtree, right? But that's apparently it's a n squared time complexity, right? And then it will TLE, right? In our case. So how do we improve that? Actually, we already picked that solution a little bit, which is that actually it doesn't really matter what the tree is, right? It doesn't really matter as if there's no 1, right? Then every node will have the answer 1, right? So only whenever 1 exists, then that's when we need to check, okay, so what are the next available missing number here, right? So what does it mean? It means that like this. So let's say 1 is here. So let's say this is 1, okay? Then it means all the parents of 1, all the parent node of 1 needs to be needs to be considered, because otherwise, if for this one, for this kind of other branches or other subtrees, there would, the answer for them will definitely be 1, right? Only the path that includes 1 needs to be updated, right? And so that's why we can just simply use like a visited node list, right, to record all the nodes we have visited for the current node, right? And then after that, right, we can just use a single while loop to check, to loop through from 1 to the max number to see what's going to be the max number, the first missing number for the current node, right? And after visiting this, setting this visited, we don't have to do the while loop for all the nodes from 1 to max, because the index will always increasing for each node on this path. Because let's say for this one there could be like other nodes, okay? Yeah. So let's say here, right? So let's say at this node, right, we find out, so the first missing number for this node will be what? Will be let's say 5. Okay, right? And then when we go back to this node, right? Of course we have to do a DFS to mark all the possible all the visited nodes for this subtree, right? That's why we need another DFS. So let's say we have already figured out, so the first missing number for this node is 5. So when we come back to here, we don't have to start from 1 to 5, because this one already includes this subtree, right? So the missing number can only be greater than 5. I mean, sorry, not greater, but equal or greater. So this one could also be 5, right? But it cannot, it would definitely not possible be from 1 to 4, right? Because 1 to 4 has already been included in this subtree here, because this subtree will also be included in this higher parent, right? That's why when I say for each of the parent node, when we try to find the missing numbers, the index will always be increasing. So it's going to be a global index here. That's why we will not uh, fall into another n squared time complexity. Right, so basically, so our logic will be, we do a DFS, right, and then for each DFS, for each current node, we do a so on the very outer for loop here, we start from the 1, right? Like I said, only the parents on the path of 1 needs to be recalculated, right? So, and every time we find a node on the path of the 1 here, we do a DFS of this node, which means we need a DFS to mark all the visited nodes or all the visited numbers, right, for this subtree here, right? And after that, we do a while loop here to find the first missing index, first missing number for the subtree, okay? And then we keep going until we reach the end, and that will be our answer, our solution, right? Okay, cool. So time to code. Let's define the DFS first. How about that? So DFS is pretty straightforward. So this current one is what? Is the is index. Okay, let's leave this DFS for later. Let's do this. Let's handle the special case first. Okay, it means that if one not in the nums, okay, we return this. Right, so that's a special case, which is the example 3 here, right? Otherwise, okay, since we need to do a DFS and the tree is given in the form of parents, we need like this is basically, this parents is a bottom up, right? But when we do a DFS, we need a top down, which means we need to create a regular tree, right? So I'm just create trees equal to the default as a list, okay, right? So this is going to be actually the children, right? So for I dot p in enumerate of parents, right? So we do a trees dot the parents, a child is parent is I, right? So that's that. And then we have the top down tree created. Now we can do our while loop here. So let's do a current node. So the current node will be the nums dot index of 1. So basically this is our starting point, right? We start from the 1 here, and then we also need a visited set, right? It's gonna be a false. At beginning everything is false, and then the length of this is gonna be a max of nums plus 2. So the plus 1 is what? Plus 1 is the visited here, the node here is what is 0 based, right? And the number is 1 based, right? So that's why the plus 1, it means that, you know, in order for us to cover all the max numbers here, we need to do a plus 1. And why do we need a plus 2 here? So another plus 1 is for what? It's for, let's say let's say the node is like 1, 2, 3, 4, right? So let's say all 1, 2, 3, 4 has already been visited. So actually, and then which means the root node, the answer for root node is 5 in this case, right? So if the answer is 5, and if the max value is 4, right? If we do a plus 1, and then the length of this one will be 5, right? But 5 is not the but if we want to use the value of 5 here, that's why we need the length of 6, right? Because index 5 will be the length of 6, right? That's why we need to do a plus 1, then plus 1 again to this one. Or you can just allocate 10 to the power of 5 plus 5 or plus 10 something. But this is, we're just trying to minimize the space usage here. Okay, and then the answer at the beginning, everything is 1, right? So that's the base case. And okay, and then we need a current number. A missing number. How about this one? Current missing number is going to be 1. Actually, this is going to be our monotonic increasing missing number. Okay, so now we have a while loop here. So while the node current node is not equal to -1, right? And we'll do a DFS of the current node, right? After this one, we do a while loop here. We have while the current missing number is not visited, it's visited, and then we increase the current missing number, right, by 1. So after this while loop, we have the final answer for the current node, which is the current node equals the current missing number, right? And then here we do a current node equals the parent of the current node, right? So that's that, and then we return the answer. So we do a DFS. So here we mark, right, all the numbers for subtree, right, rooted at current node, right? So here we check first missing number, right, for the current subtree, right? Here we just do what we move to the next parent, right? So now the DFS. So DFS, nothing's we do so visited, right? So we have visited of nums of current, right? So remember so current is the index, but we are marking the numbers, the values of this node, which is the numbers of current equals to true, right? Then we do a for child in trees, right, of the current. We do a DFS of the child, right? But here, you know, there's a like issue here. We cannot we shouldn't blindly do this because when we are like to have this kind of tree here, right? Since we're doing like this kind of bottom up the DFS, right? So when we're at here, right? So everything under this node has already been marked to true, right? To visited, And if we come back here, right, if we do a DFS again, right, then we don't want to reprocess this subtree, right? So that's why we can simply do a check here. We only continue when the current node is not being visited and marked as true, right? So this can avoid duplicate process, right, of the same subtree under the new parent. Okay, right? So I think that's it, right? So if I run the code, I accept it, I run it again. Yeah, there you go, right? So that's it. And the time complexity for this one is what? It's O(n), right? So here we have an n here. So for the while loop here, uh, so for the while loop, since we have this kind of if check here, so basically the worst case scenario is that every node will be marked to visited once, right? And then we have also have a while loop here. But again, so this while loop, since this current missing number will always be increasing, so the total number of while loop, the inner while loop is also n. That's why the time complexity for this solution is O of n, right? Mm, yeah, I think that's it. I mean, for this one, I think the only tricky part is that you need to realize that only the path that include one matters, right? That's why the starting point for our solution is the index of node one, and then we go backwards, right? Try to include all the node visited of the parent node, and then we just do another while loop to find the first missing number. Cool. I think that's it for this one, and thank you for watching the video, guys, and stay tuned. See you guys soon. Bye bye.